Hi there. In this video, we're going to be talking about partial properties, and we're going to do the derivation of the Gibbs-Duhem relation or the Gibbs-Duhem equation. So in a previous video, what I had done was the derivation of the fundamental property relation. And what we had seen in the fundamental property relation was that we can take the Gibbs energy or the differential change in the Gibbs energy of some kind of system and relate it to its canonical variables, which we saw was pressure, temperature, and the number of moles that's changing in the system if it is an open system. So we had seen that what had driven changes in these canonical variables were the drivers for these variables. So in other words, we can say that a change in the Gibbs energy, we can either relate it to the change in pressure, change in temperature, and change in the number of moles if the other variables are kept constant and there is something driving that change. For example, we had said that what drives the change in pressure is volume. And then we had said that day ng day P at constant temperature and number of moles is equal to volume. So this particular term was VdP. So you can go back to that video and check up on all of these details. However, it's important to understand those details to progress forward in the discussion about partial properties and the Gibbs-Duhem relation. We had seen that there was a change in the number of moles that also relates to the change in the Gibbs energy. And what drives this change in the number of moles is the rate of change of the Gibbs energy of the system with respect to the number of mole of each component. And we had given that a name. We had said that the rate of change of the Gibbs energy with the number of moles of a certain component or a certain chemical species at constant temperature and pressure, we had said that this is equal to the chemical potential of that particular species. So it would be a convenient place to actually start talking about partial properties from here. Because what we can now do is that we can understand and realize that we can write this relationship, what we call the fundamental property relation, not just for the Gibbs energy, but we can write it for a whole host of properties, or rather energies. For example, the internal energy, the enthalpy, the Helmholtz free energy, and also the Gibbs energy. We can replace any of these energies in terms of this equation, and we will literally have the same format. So what we'll do is that we'll have a generic property M. So we'll call that M, and we'll say that M can take on any one of these quantities. So let's replace this G with M, where M is some kind of generic property. So we've done it there, so we'll do it here as well. And here as well. So we have this relationship. So now let's define what a partial property is. So we say that a partial property, how it's defined mathematically, as the rate of change of this generic property. So that's M. So N is the number of moles, by the way. So it means that this generic property that we've written is actually a molar property. For example, if it's enthalpy, then it would have the units of maybe something like kilojoules per mole. So we have to multiply it by the number of moles to get it just in terms of kilojoules, which is the unit of energy. So what we've said now that a partial property, how we're defining it, is whatever this property is, this generic property M, we're going to take that and we're going to take the derivative of that with respect to a changing number of moles of a certain component or chemical species at a certain temperature and pressure, at a constant temperature and pressure, and we call that partial property. So we write a partial property as the property, which in this case in M, we put a bar on top, and we say that it is with reference to a particular property. So a partial property is the rate at which that particular property changes if we add a certain amount of moles of something to this property. So an easy way to think about this is, let's just say we have a glass of ethanol plus water. So it's a glass of ethanol plus water, and let's just say that there is maybe 100 milliliters of this mixture in this glass. So in this glass, there is a 100 milliliters of ethanol plus water. It's a mixture. So let's just say now we're talking about M, and M refers to the volume of the mixture. Let's just say now we're just saying that this generic property M, whatever it is the volume of the mixture, which we said is 100 milliliters. So what would be this partial property? We're saying that the rate of change, so this is partial molar volume, so the rate at which this volume changes if we add a certain component to it, and let's just say that component is ethanol, and this was equal to the partial molar volume, we'll say V with a bar on top, of ethanol. So in other words, we are asking by how much will the volume of this ethanol and water change? By how much will this 100 milliliters change if we add 1 mole of pure ethanol to this mixture? So in this glass, there is 100 milliliters of ethanol and water. We don't know the compositions. We're just saying arbitrarily this is the case. And if we were to add 1 mole of pure ethanol to this mixture, by how much will this 100 milliliters change? So that is what, when we say partial molar volume, and we can extend that and also apply it to any of these properties. Let's just say enthalpy. So in this mixture, there is enthalpy of this mixture. And now we're asking, if we add 1 mole of pure ethanol to this mixture, by how much will the enthalpy of this mixture change? So day NH of this mixture, day N of ethanol, is equal to the partial molar enthalpy of ethanol. So that's what we are saying. And we, in the same way, we also have a partial molar volume, partial molar enthalpy of water. So just as this is for ethanol, we'll also have it for water. So one would expect, what many people might expect is that, okay, if we have 100 milliliters of this particular mixture, if we just add 1 mole of ethanol to it, we can calculate the volume of 1 mole of ethanol. Will it not simply be just this 100 milliliters plus how much of ethanol we've added? Let's just say we add 10 milliliters of pure ethanol to this mixture. Does it necessarily mean that we would get 110 milliliters of solution or mixture? Well, it does not mean that. And the reason why is because there are intermolecular forces between ethanol and water that actually physically affects the amount of space that these molecules occupy at a molecular level. So 100 milliliters of ethanol plus water, and then we add to this 10 milliliters of ethanol, pure ethanol. It does not mean, it's not equal, it does not mean that we will get 110 milliliters of this mixture. But if, on the other hand, if we had 100 milliliters of pure ethanol and we added 10 milliliters of pure ethanol to that, then yes, it will mean that we will get 110 milliliters of pure ethanol, because in this case here, the intermolecular actions are between ethanol and ethanol. So just to repeat that once more, if I have 100 milliliters of ethanol, and if I add 10 milliliters of ethanol to that, then yes, I will get 110 milliliters of ethanol. So this relates to the concept of ideal solutions and like-like interactions and the different interactions between the various molecules. And then it goes back to another concept called excess properties, which we shall talk about in future videos. So bearing all this in mind, and now we have seen that partial properties is how much this mixture property M changes by, or the system property M, whatever it is, be it molar volume, molar enthalpy, or whatever. We've seen that the partial property is how much this mixture property changes by if we add a certain amount of a pure component. So we've already seen when we did the fundamental property relation that we called the chemical potential the rate at which the Gibbs energy changes if we add certain number of moles of a certain component or chemical species to it. So what this actually means is that the chemical potential, we can call that the partial molar Gibbs energy of whatever that chemical species was. So that's another point to make here. So what we're going to do is use all of this information to now go about deriving the Gibbs-Duhem relations, or the Gibbs-Duhem equations. So where are we going to So we start with the fundamental property relation. Firstly, we see on the left-hand side of this equation, what we're going to do is expand the left-hand side in terms of the product rule. So dnm, we can just replace that with ndm plus mdn. Then on the right-hand side, we see this ni. So this ni, we can replace that with xin, because ni is essentially the number of moles of that particular component or chemical species. So it's basically the mole fraction, xi, multiplied by the total number of moles of whatever is inside the system. So we can expand this out using the product rule as well. So it's dxi expanded using the product rule. So what this gives us is xi dni plus n dxi. Okay, let me just bring the screen a little bit more to the left so you can see it in its entirety. Yes, there we go. So just to summarize once more, all that we have done is we have simply replaced n. We have n here, and we said n was xin, and then we expanded this out using the product rule. So what we're going to do now is we're going to gather some of these terms and take some of these terms as a common factor. We're going to collect n and dn as common factors inside of this entire equation, both of the left and right hand sides. So let's gather n as a common factor. So we have n into, firstly we have dm, that's the first term. And then now with these other terms, we can see that n is constant, n is a constant variable. So we can bring n out of this derivative, we can bring it in front here as well. So we can bring out this n and we can write it here since it's a constant. The only difference is here n is not exactly a constant because we have the number of moles changing. So in any case, we can gather these terms. So we bring them onto the left-hand side. So we have minus, we have day m, day p, which is this term. And in this particular derivative, we have temperature and the number of moles being kept constant. And then also we have day m now, day t, and pressure and the number of moles are kept constant. And what else? Okay, we have n here associated with this dxi. So also from our definition of partial properties, we have defined partial properties as essentially being the change by which the property changes with the number of moles. So we say that whole derivative, we call that m bar I. So with the bar on top, meaning that it is a partial property. So we have m bar I times dxi times n, and now we bring that to the other side, we take it as a common factor. So what this means is that we have minus the sum of m bar I, the partial property, times dxi. And then now we're also going to gather this dn as a common factor. So when we do that, what we're left with is, well, firstly we have this m, and we also have this xi, so this should be an xi here, there's an I there, this xi times dni times this partial property. So we have minus, because we took it to the other side, so we have minus the sum of xi times this m bar I, partial property. And all of this is equal to 0, okay, because we have left nothing on the right-hand side. So we can look at this and we can analyze some things. Firstly, we see that the terms in brackets, which is that and all of this, they both have to equal to 0 because this entire equation is equal to 0. So let's start with this one. So what we're saying is that m is equal to the sum of xi times m bar I. So what is this telling us? What it's telling us is that this total mixture property is simply equal to the sum of the composition times the partial property. For example, here we said the volume of the mixture in this example with the water and this ethanol. So we said the volume of the mixture. What this is equal to is the sum of xi, which is either the water or the ethanol, times the partial property, times the partial molar volume. So that's Vi with the bar on top, partial molar volume. We can replace this summation for this particular example. So we can say that it's the composition of ethanol in the mixture times the partial molar volume of ethanol plus the composition of water times the partial molar volume of water. So we have established this particular relation here. So if we take this m, we can take a differential of this m, this total property. If we do that and we apply the product rule here, what we're going to get is the sum, firstly of xi, then times dm bar I, and then plus the sum of m bar I times dxi. And what do we have here? We have dm. So we can take this and we can substitute in here. And we also know that this part in brackets is equal to 0. So let's do that. So if we do that, then we're going to get whatever this is. So it's equal to this sum of xi dm bar I. That's this first part. Then plus this sum of mi bar times dxi, the second part. And then we write what's left. So we have minus dm dp, and this is at constant temperature and number of moles. And then we have what's left. Sorry, this should be a minus. Then we have dm dt at constant pressure and number of moles. And then we have minus the sum of m bar I times dxi. So what do we see? We see that this term and this term are actually equal, and we have a plus and a minus. So they essentially both become 0. So all we then do is write what's left, and we should also note that this entire term is equal to 0. This left-hand side is equal to 0. So if we write what's left and just take the terms to the other side, then we have dm dp at constant temperature and number of moles, and then we have plus dm dt at constant pressure and number of moles, and then we have minus this term here. So this is because we took it to the other side. Then we have minus the sum of xi times dm bar I. This is the differential change in the partial molar property. So this equation equal to 0. So this equation is what we call the Gibbs-Duhem equation or Gibbs-Duhem relations. So in the course of this video, I started with the fundamental property relationship. So I can just go back up to that. And then using this, I explained what partial properties are, and I used the example of water and ethanol to explain physically what it means. and then I proceeded to explain how the Gibbs-Duhem relation is actually derived. And it just involves just some basic maths of just finding the product rules of some of the terms, gathering some of the terms together, realizing that some of these terms are equal to 0, and then establishing the Gibbs-Duhem equation. Thank you very much for watching.